In this video, we will learn about the definite integral and the Riemann sum. The definite integral is used to compute areas under a curve. And so here I have drawn you another curve. And we have seen in previous videos that the idea is to build rectangles which are sitting a little bit inside or maybe a little bit outside of this curve, but which give a good approximation of the area under the curve. And to be more specific now, I will call the endpoints here A and B. So 0 is A, 2 is B. And then I subdivide this interval AB into n subintervals. So let's maybe do one here, and 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 one here. And then A I call x0. The next point is x1, x2, x3, x4, x5. And B would be x6. So here I have 6 intervals. So I make n subintervals of size, and then I call this delta x. So delta x is b minus a divided by n. Okay, so then n times delta x is the whole length, which is b minus a. And then in each of these subintervals, so let's maybe draw the rectangle on x3 and x4. So here, okay. Then I take a sample point, which I call xi star. So I use sample points in each subinterval. I call them xi star, and this is in the interval xi minus 1 to xi. Okay? So for example, x4 star would be in the interval between x3 and x4, but it can also be equal to one of the endpoints. With this notation, I can define the definite integral of f from a to b. And here it is. So the definite integral of f from a to b is the integral from a to b f of x dx. And this is the limit as n goes to infinity of a sum I is 1 to n f of x I star delta x. So this is quite a formula. Let's look at it a bit more careful. So the first limit here, as n goes to infinity, this means I'm using more and more subintervals. Okay, and if I use more and more subintervals, I make the subintervals smaller. So I get a finer and finer approximation to the area. So that's what the limit means. It makes it finer and finer. Now this big sigma sign here, this is the summation sign. And I will on the next slide explain you a little bit more about the summation sign. For now, just understand that this means we sum up all these little areas of the rectangles. So this is area of rectangles. xi star is the sample point, delta x is the interval length. So let's look at this on the next slide in a bit more detail. So in this definition of the definite integral, there are many, many symbols happening. So the first symbol, this sigma, is of course the integral sign. Now this is the same integral sign as you know from the indefinite integral or from the antiderivative. And we will see later that indeed it makes a lot of sense to use the same symbol because these things are very closely related. So the area under a curve is closely related to the antiderivative. And this is in fact the fundamental theorem of calculus. We get to that later. So the point A is called the lower limit of the integral, B is called the upper limit. And then this summation sign. So the summation sign indicates you should build the sum of the expressions which follow. And then there is an index involved, which is I is 1 to n. And this tells you how you should do the summation. Okay, so this is the summation sign or symbol. And for example, if I do sum is I equals 1 to n of I square. Okay? Then I have to run the index I from 1 to n and replace it in the expression. So meaning, if I is 1, then I have 1 square. If I is 2, then I have plus 2 square. If I is 3, then I have plus 3 square plus plus, and the last one is called n, so then plus n square. So I build the sum of all these expressions where the I arises as a symbol. And so then we use it here. So this is called the Riemann sum, a very important object. So it sums the area of all the rectangles. Okay, and then over all I, which means over all rectangles which we have built. So let's come back to the sample points. I started with having sample points xi star in the interval xi minus 1 to xi to build the Riemann sum. And indeed we have lots of choices for the sample point. And we can take it to be the left boundary point or the right boundary point or the midpoint or anything else. And then each choice leads us to a different rule. So for example, the right point rule here, there we choose xi star to be xi, which means the right boundary point of the subinterval. And then I call Rn the Riemann sum using the right point, which is written here. In the left point rule, however, I use xi star to be xi minus 1, which is the left endpoint of the subinterval. I call the left point Riemann sum as Ln. And then here I have the midpoint rule, which is also important. So I take xi minus 1 plus xi over 2, which is the midpoint. And then I can write down the Riemann sum for the midpoint, which gives me the midpoint rule. Now, if I let n go to infinity and make all these subdivisions finer and finer, and if the integral exists, then all three methods give me the same value. So that's written here. If the integral exists, then the integral a to b f of x dx is the limit n to infinity of the Rn, which is equal to the limit n to infinity of the Ln, which is equal to the limit of the n to infinity of the Mn. And so you will be expected to be able to compute any of these rules, the right point rule, the left point rule, the midpoint rule, for a reasonable amount of subintervals, so let's say up to 10. So let's do an example together where we can practice this. So here's the example. The function is x times e to the minus x, and it is plotted out right here. Use the Riemann sum with 6 subintervals and the left point rule to approximate the integral from 0 to 2 x e to the minus x dx. So we need 6 subintervals, so let's try to plot this out here. So here, and maybe here, and here, and here, and here, and here, and here. So then x0 is 0, and then this is x1, x2, x3, x4, x5, and x6 is equal to 2, and I have 6 subintervals. Then the interval length, delta x, this was defined to be b minus a divided by 6, okay, which is 2 divided by 6, which is 1/3. So the distance of all these subintervals is 1/3. And where are they located? So let's compute x0. So x0 is 0, x1 is 1/3, x2 is 2/3, x3 is then equal to 1, x4 is sitting at 4/3, x5 is sitting at 5/3, and x6 is equal to 2. Perfect. So now we would like to use the left point rule. So let's go back a slide and look at the left point rule. So here's the left point rule. So we need the sample points xi star, which is the xi minus 1s. And then we need to sum it all up with the strange summation sign and the delta x. Okay, so we need the sample points. x1 star is the left boundary point. The left boundary point is actually x0. Okay, x2 star is the left boundary of that subinterval, which is x1. And looking above, as x1 is 1/3. x3 star would be x2, which is 2/3, and so on. x4 star is equal to 1. x5 star is 4/3, and x6 star is 5/3. Now we need to compute the function values f at those sample points. So we need to find f at xi star. And I prepared a little table here on the next slide. So here I have the index I. Here I have the sample point xi star, which is the left point of the subintervals. And then here is the function value at these points. Well, you just take maybe 1/3, sub it in, and you get 0.239. Now we are ready to compute L6. So what is L6? That was the sum of I is 1 to 6. Function evaluated at the sample points times the interval length delta x. Okay, and so now we got everything together. So the index I runs from 1 to 6, which means we need to sum all of these terms. So then the first term would be a 0 actually, and then times delta x, and delta x is 1/3. And then plus 0.239 times 1/3. And then plus 0.342 times 1/3. And then plus 0.368 times 1/3, plus 0.351 times 1/3, and then plus 0.315 times 1/3. So at this stage, it is actually rather easy. Just write down these numbers. Now you have a sum, and you have a calculator, and you put it all together, and then we get 0.533 for L6. So that would be our approximation. So then we can say integral from 0 to 2 x e to the minus x dx is approximately equal to 0.533. Now if we want to get a better approximation, we use L7 or L8 or L100 or L10,000. Or as we have seen, we can use the right point rule, so maybe R1000, or the midpoint rule M1,000,000. Now on a side, we can actually find the exact solution of this to be 0.594. Okay? So we do a good approximation, but we could also do better. And how to find the exact solution, this is something which we will learn much later. Coming back to the example, this means that the area under the curve from 0 to 2, so meaning this area here, is approximately L6, which was 0.533, and the exact value is 0.594. So this here. So let me summarize. So this sum I is 1 to n f of x I star delta x is called the Riemann sum, and the definite integral is defined as a limit of these Riemann sums. And it is a limit for n to infinity, meaning the subdivision becomes finer and finer, and we get closer and closer to the integral. The most common choices for the Riemann sum are the left point rule, the right point rule, and the midpoint rule. Oh, hello, Dr. Riemann. How are you doing? Very nice to meet you. What are you up to? Oh, very interesting. I wonder which one of these we can use in our calculus class.